In the previous lecture, we had started our discussion of forced convection under conditions of high Peclet number. Okay. The simplest case we had considered is the flow past a flat plate. Okay. It consisted of a flat plate along the x axis at z is equal to 0, in which the heating section started at x is equal to 0. Okay. The heating section of the flat plate started at x is equal to 0 and the extent of this heating section was L. Okay. Therefore, the temperature was T infinity for x less than 0 and for z going to infinity. Okay. So, it was T infinity for x less than 0 and for z going to infinity, and only at z is equal to 0 for x greater than 0 when there is heating from the plate, the temperature was equal to T w. Okay. We had written the equation, the convection diffusion equation, as you can see over here. Okay. Partial Vx partial T by partial x is equal to alpha into the Laplacian of the temperature, scaled all the lengths by L and the velocity by the characteristic length scale, and we had an equation of this kind. Okay. So, Vc times L by alpha is the Peclet number. Okay. In the limit of Peclet number becoming large, you can divide the equation throughout by the Peclet number, and you just get this simple condition that Vx times partial T by partial x is equal to 0. Okay. This just states that the temperature is 0 everywhere. The scale temperature is 0 everywhere because the scale temperature is 0 upstream and it is independent of x. So, basically the scale temperature is a constant along streamlines, and since all the streamlines originate at x becoming x less than 0, okay, therefore, the temperature has to be 0 everywhere. This obviously does not satisfy the boundary condition that there is heating at the plate. Okay. And we had examined the method by which we can satisfy the boundary condition. Mathematically, it cannot be satisfied because we have converted from a second order differential equation to a 0th order equation in the cross stream direction. The original problem was a second order differential equation in the cross stream direction, and two boundary conditions could be satisfied. The simplified problem in the high Peclet number limit was a 0th order differential equation. Therefore, you could not satisfy the boundary conditions. Physically, this was because the temperature at a location is determined by a balance between the streamwise convection and the cross stream diffusion, and the cross stream diffusion of heat from the heated section causes a disturbance to the temperature. If you neglect the cross stream diffusion altogether, there will be no change in the temperature. That is what we get by neglecting diffusion altogether. Physically, the heat that is diffusing from the surface gets rapidly convected downstream due to the strong flow in the limit of high Peclet number, and it is necessary to include diffusion within a region that is much thinner than the characteristic length scale in order to get a balance between convection and diffusion. Okay. And we had seen how to do that. Okay. We had to scale our z coordinate by delta. Okay. We had to scale our z coordinate by delta, which is much smaller than L, rewrite the equations, and then determine delta from the condition that convection and cross stream diffusion are comparable within this region of thickness delta. Okay. And from that we had got the solution that the thickness of this region has to scale as the Peclet number to the minus 1/3, where the Peclet number is based upon the strain rate at the wall and the length square. Okay. It is based upon the strain rate at the wall and the length square. Okay. And if you do that, as P goes to infinity, delta becomes smaller and smaller, but convection and diffusion continue to be of equal magnitude within this boundary layer region. Okay. Then we were trying to look at ways to solve the problem. Okay. So, let me first explain the rationale for the solution. Okay, so I have this. Okay. This is x is equal to 0. Okay. T star is equal to 1. T star is equal to 0. I am assuming that I have already scaled my temperature, okay, because it is a constant factor when you scale the temperature. And T star is equal to 0 far from the surface. Okay, so this is the start of the heating section. And the equation, let me just write it again, when you include only streamwise convection and cross stream diffusion is Vx partial T by partial x is equal to alpha into partial square T by partial z square. Okay. I have neglected the streamwise convection in comparison to the cross stream. I am sorry, I have neglected the streamwise diffusion in comparison to the cross stream diffusion, okay, because I expect a balance between streamwise convection and cross stream diffusion. How do I determine the temperature field from this? Okay. At a given location x, say, okay, at a given location x, okay, there is streamwise convection that is transporting. Before that, let me also mention that the total length of the plate in this case is equal to L. Okay, the total length of this heated section, the total length of this heated section is L. That is the length scale in the problem. At a given location x, okay, within this boundary layer, the region where there is a disturbance to the temperature due to the heating, there is streamwise convection and cross stream diffusion. Okay. Streamwise convection transports fluid downstream, okay, and cross stream diffusion is perpendicular to the surface. Therefore, the temperature at a location x depends only upon x itself and not on the total length L, okay, because streamwise convection is transporting the material, the heat downstream, and cross stream diffusion is transporting heat across the flow. Okay. At a given location x, the temperature at that location x should not depend upon the total distance L, because that downstream edge of the heated section is downstream of this region. Convection is downstream, and therefore, there is no way for the temperature field downstream to affect at a location x, which is upstream. There is no diffusion and convection is downstream. Diffusion is only in the z direction and there is no diffusion in the x direction. Okay, so therefore, I can assume that at a given location x, the temperature field depends only upon the distance x itself and not on the distance L. Okay. At a given location x, the temperature field depends only upon the location x itself and not on the total length of the plate L. Okay. Therefore, the thickness of this region over which there is a balance between convection and diffusion, okay, the distance thickness of this region over which there is a balance between convection and diffusion will depend only upon the distance x. Okay. So, I will call this as, okay, I will call this distance as delta x, which is a function of x, okay, the thickness of this region over which there is a balance between convection and diffusion. It depends upon x, of course, but it cannot depend upon the total length L. Okay. So, therefore, I can define a similarity variable eta, okay, is equal to z by delta x of x. Eta is equal to z by delta x of x. And the temperature, okay, the scale temperature in this case, okay, depends upon x and z only through the dependence of the temperature on eta. Okay. The temperature depends upon x and z only through the dependence of the temperature on eta. Okay. So, why can I postulate this? First thing, there is no length scale in the cross stream direction. Okay. I have assumed that the fluid is of infinite extent in the cross stream direction. So, there is no length scale there. Even if there were a length scale in the cross stream direction, so long as the boundary layer thickness is much smaller than that length scale, you can assume that it is only delta that matters as far as the temperature field is not concerned, and not the total extent in the cross stream direction. There is a length scale in the streamwise direction, but when convection is strong, convection transports heat only downstream. Diffusion has been neglected. Okay. Diffusion acts in both the upstream and downstream directions, but streamwise diffusion has been neglected. So, therefore, there can be no influence of the total length of the plate, okay, which is downstream of the location x, on the boundary layer thickness at a given location x. Even if I changed L, okay, the boundary layer thickness at the location x will not change. Okay. So, that is the physical rationale for this similarity solution. And I need to determine what is this delta x in such a way that convection and diffusion are comparable, and the temperature field expressed in terms of eta, the similarity variable, is only a function of eta and does not depend separately on x and z. Okay. So, that is the rationale that will be used. So, how do I have to first substitute for t of x in terms of as a function of eta, okay, into the equation and get a simplified equation, and within that find out the condition under which the equation and the boundary conditions depend only upon eta and not individually on x and z. Okay. So, let us do that. This is done by chain rule for differentiation. Okay. So, partial t star by partial z is equal to, okay, partial eta by partial z dt star by d eta. Note the total derivative with respect to eta, because I am postulating that the temperature field depends only upon the similarity variable eta and not separately on x and z. Okay. There is the derivative in the z direction. Okay. I need a second derivative in this conservation equation. Okay. So, I can get that second derivative, okay, partial square t star by partial z square is equal to is equal to 1 by delta x square t square t star. Okay. Using chain rule for differentiation. Okay. I have a first derivative with respect to x. Okay. Note that eta is z by delta x and delta x is a function of x. So, I have to use chain rule for differentiation. I will get this as minus z by delta x square d delta x by dx. And since z by delta is eta itself, I will get minus eta by delta x d delta x by dx dt star by d eta. note the total derivative of delta x with respect to x, because delta x is only a function of x. Okay. And finally, I also have to substitute the expression for Vx. Okay. Vx close to the surface is Vs prime z, okay, where Vs prime is the strain rate at the surface dVx by dz at z is equal to 0. Okay. And I can write this as Vs prime delta x times eta. Okay. Substitute into the equation. Okay. Substitute into the equation. Equation is here. Vx dt by partial t by partial x is alpha times partial square t by partial z square. Substitute these derivatives. Okay. Vs prime delta eta into minus eta by delta x d delta x by dx. Okay. This should be delta x. Okay, into dt by d eta is equal to alpha by delta x square d square d by d eta square. And in order to get a differential equation, I divide throughout by this prefactor. Divide throughout by this prefactor. Okay. And I will get here Vs prime, okay, times, okay, delta x square, okay, by alpha d delta x by dx, okay, into minus eta dt by d eta. Okay. I am sorry, eta square. So, this is the differential equation for T star in terms of eta. Okay. And this equation is only a function of eta if this term here is a constant. Okay. If this term here is a constant, then the equation is only a function of eta. Okay. Okay. So, a similarity solution can be used only if this term is a constant, okay, which is Vs prime delta x square by alpha d delta x by dx is equal to some constant. I will call it as c delta. Okay. So, if this is a constant, then the equation is independent of x and z. It depends on x and z only through the dependence on eta, okay, or if this is a constant. It turns out that the value of this constant does not matter. I will show you that in a little while, that the value of this constant does not matter. The temperature field expressed in terms of eta, the similarity variable, does depend on this constant. The temperature field expressed in terms of the original variables x and z does not depend on this constant. Okay. So, we can in general set the constant to any value, okay, and usually this constant is set equal to 1. I will solve this problem with some unknown value for this constant and then show you that the final expression does not depend upon the value of the constant. Okay. Okay. So, that is as far as the equations are concerned. Okay. So, this is the equation. What about the boundary condition? Okay. Okay. At okay, as z goes to infinity, okay, T star is equal to 0. Okay. Z is equal to z by delta x is eta. So, as z goes to infinity, this implies that eta goes to infinity. Okay. At z is equal to 0, the temperature, scale temperature is equal to 1. Okay. Note that the temperature was the wall temperature and the scale temperature is 1. Okay. Z is equal to 0, eta is z by delta. Okay. So, this implies that eta is equal to 0. Okay. So, that is the boundary condition in the eta direction. Okay. And the other condition was that at the start of the heating section, the temperature was equal to T infinity throughout the fluid, okay, because it had just entered the heating section, and that at that location there had been no heat transfer yet, okay, at the start of the heating section. Therefore, the temperature should be the undisturbed temperature T infinity, or T star is equal to 0. Okay. At x is equal to 0 for, okay, z greater than 0, okay, T star is equal to 0, okay, at the start of the heating section. Okay. What does this correspond to? Okay, at the start of the heating section, there has not been any heat transfer yet. That means that the boundary layer thickness, the region over which there is a disturbance due to the heating from the heated plate, has to decrease to 0. Okay. That means delta x has to decrease to 0. Eta is z by delta x, okay, and therefore, that means that z by is greater than 0, delta x is equal to 0, means that eta goes to infinity. Okay, eta goes to infinity. Okay. Okay. Note that the original problem was first order in x and second order in z. So, we had two boundary conditions in z and one in x. When we made the similarity transform, there was only two, it is a second order equation in eta. That means that there can be only two boundary conditions in eta. Okay. And as you can see, the two of the conditions, one for z going to infinity, the other at the start of the contracting section x is equal to 0, these two turn out to be identical when expressed in terms of eta. Okay. So, this problem is well posed. We have two unique boundary conditions, one at eta is equal to 0, the other for eta going to infinity. Okay. So, those are the equations and the different and the boundary conditions, and we have to now solve this equation. Okay. There are two things here. One is this differential equation. Okay. One is this differential equation, which gives delta x as a function of x. The second is the equation for t in terms of eta, okay, c delta eta square dt star by d eta, the negative sign is equal to so, first we have to solve t in terms of eta and then delta of x as a function of x, and put those two together to get the final solution. Okay. So, that is the procedure. Okay. So, first let us solve the equation for eta. Okay. So, you can do the substitution, w is equal to dt star by d eta, okay, the first derivative. Okay. So, I will get minus c delta eta square w is equal to dw by d eta. Okay. Integrate once, minus eta square d eta is equal to dw by w. Okay. Okay. Which implies that the natural logarithm of w is equal to c delta eta cubed by 3. with a negative sign. Okay. Which means that and therefore T star is equal to I'm sorry, this is plus a constant, okay, a constant of integration, okay. Therefore, this will have a constant of integration pre-multiplying it, okay. When I exponentiate that term, okay, I will get C1, okay, e power minus C delta eta cubed by 3, okay. And therefore, if I integrate it a second time, I will get T star is equal to C1 integral 0 to eta d eta prime e power minus C delta eta prime cubed by 3, okay, plus C2. Okay, so, that is the final solution. Okay. Let me write that again for you. T star is equal to C2 plus C1 integral 0 to eta d eta prime e power minus C delta eta prime cubed by 3, where eta prime is the variable of integration, okay, where eta prime is the variable of integration. Okay. Eta prime is the variable of integration. Now, we have to apply boundary conditions. Okay. T star is equal to 1 at, okay, z is equal to 0 or eta equal to 0, and T star is equal to 0 for z going to infinity or eta going to infinity. Okay. And using this, you can easily verify that the temperature field is of the form T star is equal to 1 minus integral 0 to eta. So, that is the expression for the temperature field. Okay. For eta going to infinity, you can see that on the second term on the right, the numerator and denominator are the same. So, T star is equal to 0. For eta equal to 0, the integral on the numerator on the second term on the right is integral from 0 to 0. An integral between two equal limits has to be 0. The area under the curve is equal to 0. Okay. So, this is the solution. Okay. And W, okay, is equal to dt star by d eta is going to be equal to e power minus C delta eta cubed by 3 by integral 0 to infinity d eta prime e power minus C delta eta prime cubed by 3. Okay, so, that is going to be the derivative. Okay. So, this should be negative sign here because of this negative sign here. integral of a function, the derivative with respect to eta of integral, where eta is the upper limit, is just the integrand at that upper limit. Okay. So, that is all we have used here. So, this is the formal solution for t as a function of eta. Okay. This is a formal solution for t star as a function of eta. Okay. We still have to calculate the solution for delta as a function of x, and once we do those two things, we can then construct the solution. Okay. So, I will say a few things about how to evaluate this integral in the denominator here. Okay. This integral. Okay. The next lecture I will say a few things about how to evaluate this integral, and then we will find out delta as a function of x, and from that find out the temperature field, the heat flux and the correlation. So, I will continue this in the next lecture. I will see you then.